Hi, my name is Rajiv Karuwat, and I will be presenting my term project on passwordless authentication using WebAuthn for my C6 604 class. A little bit about myself. I did my undergrad in electronics engineering from Mumbai University, and I passed out in 2017. And then I worked as a software developer for 3 years at BNP Paribas. And I joined RIT as a graduate student in the computing security department in this last fall 2020. So a little bit about why we need passwordless authentication. One of the main problems of passwords is where it requires that users remember complex passwords in order to get certain amount of security. So like we are putting the onus of security goes on the user side, which we know that we cannot expect a lot of normal everyday users to remember such complex passwords. Like let's look at some statistics. For example, 87% of all breaches in 2017 were caused due to password abuse. This has been in the Verizon data in breaches report. And in the same report, it also says 51% of all passwords that were breached were also found to be reused across different websites. The certain password complexity requirements, which are listed out in standards like NIST, have usability problems in that we cannot expect those users, our normal everyday users, to remember such complex passwords. So let's look at how we are currently mitigating this problem. So one of the common methods that you must have heard of is multi-factor authentication. That is, you- certain one-time passwords are sent via SMS or via push notification or generated using a hardware token like an RSA token. And that serves as the second factor of authentication, which is something that you have. So that provides an additional degree of protection. Another common thing which is seen in a lot of enterprise settings is a smart card, the Department of Defense Common Access Card standard, which basically stores a X509 certificate inside, and that is used for all crypto operations, which in turn can validate security. And the third one is security keys, which are gaining a lot more traction now, especially with companies like Ubico who are making security tokens for second factor authentication. So let's look at an overview of WebAuthn. WebAuthn in itself is a passwordless authentication protocol, which is designed to provide secure passwordless authentication by employing public key cryptography. So essentially, WebAuthn is trying to go away from passwords entirely by relying on strong, well battle-tested public key cryptography techniques and ensuring that on the user side there is very minimal requirement apart from keeping their security devices safe. It is part of the overall FIDO2 architecture, which is a successor to FIDO U2F. So, like those Ubico keys that I spoke about earlier, they were made as part of a spec called as FIDO U2F or Universal Two Factor. FIDO, or also known as it stands for Fast Identity Online, is an alliance, is a group of industry veterans like Google, Samsung, RSA, who have built, who were in the process of building a standard to make two-factor authentication a lot more palatable to everyday users. And they implemented this using the FIDO U2F standard. Now, in this context, we will call it FIDO 1. And this served as a very robust framework for using security keys as a second factor authentication. Now, WebAuthn is part of the FIDO2 spec, which aims to completely eliminate passwords by ensuring the security is inherited from the public key cryptography that is present, that can be used as part of security keys. And they have implemented the WebAuthn framework as a JavaScript API. So all browsers will be able to call browsers which support WebAuthn will be able to call the WebAuthn function calls using navigator or credentials. So in fact, like actually you can implement this any native JavaScript application that you want. And also part of the FIDO2 spec is CTAP2 or client to protocol client to authenticator protocol 2. So CTAP 2 acts as the conduit between the host, which is for example, the browser, and the authenticator itself. So it acts like it's the protocol which defines how the interaction between the how a secure interaction between the authenticator and the browser can occur. We will see more about this in the later slides. So of now we will look at a FIDO2 compliant authenticator. So an authenticator can be defined as any device which is capable of executing PKI operations in a secure and isolated environment. Basically, the core requirement is it should be able to store the private key securely. It should be able to do operations like signing, key pair generation, and in an isolated environment which cannot be tampered from the outside. So if it provides such an environment, it can qualify as an authenticator. There are two types of authenticators: roaming authenticator and platform authenticator. WebAuthn interacts with the authenticator through CTAP2, like I said earlier, and the underlying transport, like the actual interaction with the device, can happen over USB, NFC or near field communications, Bluetooth, BLE, that is Bluetooth Low Energy, and this is in case of roaming authenticators. Platform authenticators, on the other hand, are WebAuthn interacts with them using the device-specific bindings. So, for example, your laptop would most probably have TPM, a trusted platform module, which usually does stuff like secure boot and handle some of the crypto stuff which is needed for technologies like Windows Hello. Or your Android device might have some dedicated crypto chip inside it, like which maybe not dedicated crypto chip. It can also be a software implementation, like how ARM has the uh, trusted zone implementation in its instruction set, and similarly, Apple has its Apple Secure Enclave, which handles a lot of crypto applications. So these are device-specific crypto implementations. So hence they are known as platform authenticators. Roaming authenticators, on the other hand, can as the name implies, roam. That is, you can disconnect the authenticator, connect it to another host, and you can reuse that same private key which is embedded in the authenticator. So now next, let's look at how WebAuthn works. So the protocol itself has two main components: the registration ceremony, which is what we will use to register users, and the assertion ceremony or the authentication ceremony, which is how we will log in users to it. So let's first look at the registration ceremony. So the registration ceremony begins by the client requesting the server, or the relying party. In this case, the correct nomenclature for the server is the relying party, for a specific challenge and certain information, like what sort of public key algorithms do you support, etc., that kind of stuff. So server responds with a challenge. Now this challenge is usually a cryptographically secure pseudo random generated number of bytes. So any OS level implementation can generate these bytes for you, and the server will also respond with what all public key algorithms it supports. And there are others parameters also, which is too in depth for this presentation, but it's there as part of the spec. Now, once the client receives this information, it needs to because this is JSON, and because all this is happening over HTTP, we need to convert this from a JSON embedded um, uh, format to bytes, array bytes of JavaScript. So the client does all this conversion and it sends it to the authenticator. Now, the sending to the authenticator occurs over the CTAP2 protocol. That is this 2 that we see over here. And the client formats it in a certain way which the client authenticator expects, which the spec has already defined. The authenticator will take this information and it will generate a new key pair. It will generate attestation, which we will see later, and it will also do user verification. User verification is basically if the server requires that the user enter some sort of PIN or have some sort of knowledge which can prove the provenance of the authenticator, that the user owns the authenticator. The server can request this in form of user verification. So if the user verification flag is set to true, then the client or the person who is executing the ceremony will have to enter a PIN or a biometric login like thumbprint. Or in case of Apple, even Touch ID is a valid user verification, is a valid supported user verification endpoint. So the authenticator generates all this key pair and it returns this data back to the client. The client again receives it in form of byte arrays. Now we cannot send byte arrays directly to a server over the HTTP protocol, so we need to convert it to base 64, and this is converted to base 64 and it is sent back to the relying party. Now, the relying party can validate this information. First of all, it needs to validate the challenge, whether the challenge was not it matches the original challenge that they sent as part of the initial request. So this ensures that this mitigates replay attacks where like someone can try to intercept the request in between and try to spoof a form of or initial request. And this data is then decoded at the client side, and if all the verifications pass, the client will save this as the public key associated with the user. So let's look at some of the parameters here. It has multiple, two main things that we are that we need to focus on is the challenge and the supported public key algorithm. So here, if you see it, it supports algorithm -7, -257, -37. So these are basically INA naming conventions for public key algorithms. -7 means ECDSA with SHA-256. So that is elliptic key cryptography digital signature algorithm with SHA-256 hashing, and it returns the user information as well. And using this, the authenticator responds with a certain encoded data. So now this is again encoded. So on the server side, we will unpack it. And the important parameters of this is the, as we saw, the challenge, the origin. So the origin is a very important part in that. So for example, if the WebAuthn is getting executed from from HTTPS google.com, for example. So the google.com is the origin. So the server must be able to verify the origin to ensure that it is not being tampered with in between. And challenge, as we saw earlier, token binding is not exactly important in this case, but it is part of the spec. And ceremony type indicates whether it is a creation or like registration, or whether it is a login event. And then finally, we look at the attestation object. So the attestation object is also like it's quite there's a lot of flags here, but what is important is the auth data. So the auth data basically tells us, gives us some important information, which or out of which the most important for us is the credential ID and the associated public key of the user. So these two are the ones that we will actually save it into our database. And then we have some additional information using which we can validate whether this matches what we originally sent as part of our request. Like for example, if we requested user verification flag UV, we can ensure that the response in which the authenticator returns the UV flag is set. Or if attestation was required, we can verify that. Counter is a pretty useful value here, which basically tells us uh, how many times the authenticator has been used for this specific credential. So usually the first time when you register, the counter is 0, but every time you log in, the counter is increased. So using this, and if you maintain, if the server side, the counter is also maintained, we can track whether the counter is increasing in an expected way. So what would happen is, let's say that someone cloned the authenticator and some tried to log in with a cloned authenticator, and the legitimate user also tried to log in with the cloned authenticator, the counters would increment in a different manner. So using this, we can track whether authenticator has been cloned or not. So this can be used to like, let's say we figure out that, okay, the authenticator has been cloned. We can mark that credential as compromised and ask the user to register again. Then let's look at the authentication ceremony or the login ceremony. It's quite similar to the registration ceremony. We specify that this is the user we not need to log in as, that is the 0. Then the server responds with a challenge, and it also responds with a certain with the credential ID of the public key that it saved earlier. So the authenticator knows, okay, this is the credential ID with which they have to sign, and this is passed is in a similar fashion as the registration ceremony. This is passed to the authenticator, and this is sent back to the client, and the client will again modify, convert the byte arrays to base64 and send it back to the server. One key difference is the signature. So the signature here is the core part of the PKI aspect. So because the authenticator only has the private key, they can use a private key to generate a signature, which can be verified at the uh, server to basically confirm non-repudiation, that the the authenticator owns the private key for this particular public key that we had saved earlier. So this is essentially where the passwordless login aspect comes into play, because we are using those public keys, public and private keys to verify ownership. We do not need any passwords. Rest of the data is essentially to do some additional verifications, whether with the to increase the security, whether the parameters that we sent were matches whatever the authenticator is responding with, whether it hasn't been tampered in transit or not. So this is how the server response, the initial server response requires looks. So it responds with, okay, this is the credential ID that is saved in the server, and the underlying transport that it supports, like we saw USB, BLE, NFC, and also it gives a challenge. And the authenticator responds with this. It is a similar data structure as we saw in the registration format, but the only difference is it also gives a signature that can be verified on the server side. So in order to implement this, I built two main components. First is building a FIDO2 compliant authenticator, that is actually building the security key. Second is building a web portal which implements both the client side and the server side code. So the client side is using TypeScript Angular. The server side is built using Python Django. So building a FIDO2 compliant authenticator. So for this, I'm using Google's OpenSK framework, which can be used to build a TalkOS application. TalkOS uh, is an embedded OS framework, which basically emulates USB HID protocol. And inside that, we have Google has implemented all the security algorithms that can be compiled, and it can be flashed into this Nordic NRF 52840 dongle chip. So this chip can be this dongle can be bought, and we can flash this. So I've given a video demonstration of how the flashing process works. So we essentially boot the device into DFU mode, that is device firmware upgrade, and then I built a script to automate some of the parameters of flashing, and then it is executed and it flashes the image. So it takes some time. After the image is flashed, the authenticator is ready to be used. Commercially available authenticators are also there. So this is more of a research platform that Google has built, but there are commercially available authenticators like Ubico, etc., which can also be used. So the client side implementation. So the client side implementation of the code can be seen here. So I'm not going to go deep into the Angular side of the code. Essentially, it boils down to certain component, the reusable service that I have built, which does some of the translations. Like it, for example, start WebAuthn register. Like it takes a username, it sends it to the server. The server responds back with a challenge. We do some conversions on the challenge. Like we convert it from base64 to an 8-bit array, byte array, and then we execute something called as the act sorry but yes, yeah, we execute uh, navigator.credentials.create. So this is the actual WebAuthn API that W3C has created. And once we execute this, the data is sent to the authenticator, and the authenticator responds back with the authenticator response, which we send it to the server directly. We do some conversions. So that is what this function is for, to do some conversions, like handle the byte arrays correctly, to convert it correctly to URL base64 encoding. And this is sent to the server. So in a similar way, the same login method also works in a similar way. The key difference is, as we saw, it also has the additional signature, um, which is generated using the private key on the authenticator. And the server-side code is written in Python Django. So again, the code for all this is on my GitHub. The links are here. So if you want to check these out, the instructions to set it up locally on our development environment is also present as a readme.md file on the GitHub repository. So as you can see on the server side of the WebAuthn is implemented. So we are essentially generating the challenge using using random bytes that we get from the OS, and we use that as the challenge. Also, we also save the challenge on the server side using sessions, and we usually want to remove the extra padding which is there. This is because what happens is if you send extra padding along with your base64 encoded values, even those paddings would be converted to byte arrays, which is not which is not really accepted on the authenticator side. So we strip the padding before sending it, so that when we receive it on our end of back from when the server receives it again from the client, it is already converted. All the padding has been removed and sent. So that is why we need to, when we compare it with the challenge, we need to remove the padding before we do the comparison. Otherwise, the implementation would never work. So the final deployment, the code is deployed onto this temporary website that I've created using a Google Cloud server. The client side is, again, it's because it's Angular, it's built into artifacts and deployed on an Apache web server. The server side is served using Python Unicorn, which is an application server for uh, Python with Z applications. And all of this is brought together using an Apache reverse proxy and HTTP. So also WebAuthn requires this website be served over HTTPS. So this HTTPS of certificate was procured from Let's Encrypt. So let's look at a demonstration here of the login flow, of the registration and login flow. So here I am giving a username, and I would be entering that. Also a display name can also be given. This is not strictly necessary, but username is what we need. We click on register. So if you see here, it initially asks me to log in using my fingerprint. That is this. So this is Windows Hello, which is the platform authenticator that I talked about. So this is default behavior that it tries to log in using the platform authenticator first. But on the server side, you have the options to tell the user not to do the platform authentication, just do the the roaming authenticator. So here I'm canceling that. So it is switching over to roaming authenticator, and it asks me to enter. So this is the user verification part where it is asking me to enter the security key pin. So now I'm entering the security pin, and it asks me to touch, that is verify my presence. This is known as user presence, and I'm touching it. So that verifies it. So if you see, it gives the response here. So here, if you see the signature counter, it is 0. So that means because this is an initial registration, it returns the 0. This is the public key. This is a credential ID, which is needed. Again, like all this information is saved on the server side. And the best thing about public key cryptography is, even if all this information is leaked, if it gets breached, the user security is in no way compromised. As long as the private key on the authenticator remains safe, the user is completely secure. So now we attempt login. So we give the same, we gi- sorry, uh, we give the same username. So here we are attempting to log in using the same username. As you can see here, now it did not ask for user verification. It directly went to the security key. It did not ask for the TPM, the platform authenticator in between. This is because on the server side, the credentials are already saved and the server knows that this is from a roaming authenticator. So when it sends it to when sends the request to the client also knows it needs to use the roaming authenticator. That's why it automatically goes to the authenticator and it asks me to verify my user presence by touching the button. And as you can see, the verification is successful and it returns, as you can see here now, the signature counter has increased to 100. So that the login was successful. So now due to because these modules are a bit expensive to procure, I could get only one to test. So in order to test the scenario of a failed login, I'm going to go to the server backend and edit the database value to reflect a different security key, public key, basically emulating the fact that this user Rajiv KR was logged in using a different username, so using a different public key. Initially registered using a different public key. So now if I were to try to log in again, it would fail. The authentication would reject. It would ask me to verify. And after I give the response, it says assertion failed. So this is because the signatures won't match anymore because the public key which is saved on the server side is different, which means it was logged in using a different authenticator. So now the roaming authenticator use case where the roaming authenticator really shines. So here is an example where I am registering using a username on my laptop. So it's asking me to log in as a secure using my security key. I'm verifying my user verification and now I touch the key. Sorry. So now my registration is successful. So now I can again test the login here to verify if it logins and it logins successfully. So now what I can do is I can actually connect this security key to any other device which supports WebAuthn and it would still log me in. So here I'm connecting it to my smartphone here and I'm logging in with the same username. Now I try to attempt login and it tries to read the security key. So here I'm trying to connect the security key via USB. And first I need to give access to this USB-C dongle that I'm using. So that's why it fails the first time. But when I repeat it, it will now request access to the security key. And then I can touch the button to give user presence and see I'm logged in again successfully. So this is the use case for a roaming authenticator. Why the roaming authenticator? So like you can use this roaming authenticator to connect to anywhere. So now the USB part might be a bit unusable for users like to connect USB devices. So the as I had said before, the underlying transport supports multiple formats. Like so, USB HID is one of them. It also supports Bluetooth BLE. So there are security keys which are Bluetooth enabled. So like Google's Titan security key is an example so that you can use wirelessly with any Bluetooth enabled device. So I tested this across multiple devices and browsers. I got very significant improvements in login times compared to username password based logins. As you can see here, the attempts failed on IE11. This is because IE11 is now deprecated and the WebAuthn protocol is not supported in IE11 anymore. And it also failed on Safari Mobile on iPad OS. But this is actually not due to a fault of the protocol. This is because the dongle that I was using was not compatible with the iPad. So if there were a USB authenticator which connects via USB-C directly, it would work fine with the iPad OS as well. So for future work, like there are the WebAuthn spec is very expansive and there is a lot of things that can be implemented to improve security. The first example is TPM attestation. That is basically allowing users to use their uh, uh, trusted platform modules. That is your platform authenticator to authenticate. So This can be implemented as TPM attestation on the side on the server side. But as I said, it's not preferable because it's not portable. But there can be use cases for that. For example, business use case where a corporate entity wants to restrict access uh, uh, to a website from only certain devices. So the TPM on that device would be the only would have the private key, and using that only you can log in. You cannot log in using any other device. Account lockouts are another thing that need to be handled. So let's say that you lose your you lose your authenticator. That effectively means you've lost the private key. So there is no way for user to to request account reset, like how you would reset a password via an email. So the WebAuthn spec suggests that you should let the user, after initial registration, you should let the user register a backup key as well, and that backup key can be used when the primary key is lost. So in this, the WebAuthn, so this does not mean the private key is duplicated across two authenticators. The private keys are always distinct. It is just that the WebAuthn spec allows you to implement multiple credentials associated with a certain user. So this can be used to handle account lockout scenarios. Privacy improvements. So there are a lot of specific privacy related components that can be implemented in the WebAuthn spec to preserve user privacy in case the uh, backend database is breached. So like I said, the username we saw that the username is one initial thing that we do need to give. So that username can be considered as a privacy um, the, issue for certain people. Like so in WebAuthn, there is a specification called as resident key, which allows you to log in even without using a username. So you just need the or your authenticator and the client can decide which which username you're trying to log in for, and this username is auto generated on the server side. So it's a machine readable identifier, so that preserves the privacy in case of uh, privacy related to username issues. The BLE transport for the Nordic chip. So the underlying Nordic chip actually supports Bluetooth also. So the Google OpenSK framework can be overhauled to allow for BLE transport along with USB transport to allow like a wireless authenticator. So in summary, basically WebAuthn provides a secure and seamless authentication flow without any passwords and is privacy focused. And with more as more and more users start getting these devices, or the platform authenticators get more robust, the WebAuthn protocol will see more widespread adoption. In fact, there are production ready implementations on major companies as well. Right now Microsoft is a classic example, which allows you to log in using your Windows Hello platform, which is again WebAuthn. uh, we can expect significant reduction in authentication attacks through techniques like phishing, because there is no password involved and your device is the only authentication parameter that you would have to use. Thank you for watching my presentation.